That's showing the interlock there where it's not capable once the other one's energized. So I started that. Now that won't work, so it's electrically isolated. And when I open them up, okay. Motor counter electromotive force.
CEMF.
Which is typically counter EMF. Okay, this is what we were talking about before. I guess we talked about it a little bit when we were into AC power. The counter EMF is a form of resistance that opposes and limits the flow of armature current. Again, it opposes a coil, by definition, is a inductor. Okay, and inductance opposes changes in currents. So when currents try to change by blowing up, it tries to push it back down again. So as the armature rotates in a DC motor, the armature coil cuts the magnetic field of the stator and induces a counter voltage or a counter EMF in them. This occurs in a motor as a byproduct of motor rotation, is also referred to as the generator action of the motor. And it's essentially what takes the high inrush current and pushes it back down, because your applied voltage is being opposed by your counter EMF. All right, essentially canceling part of the applied voltage, and now you've got just a lower point at which they come into being steady state. Counter EMF is a form of resistance that opposes it, blah, 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 the motor current, blah, blah, blah. It also refers to the generator action of the motor. Okay, overall effect of the counter EMF is that the voltage will be subtracted from the terminal voltage, or applied voltage, of the motor, so that the armature motor winding will see a smaller voltage potential. Voltage applied, subtract the counter EMF, divide that resistance, and you've got that. It'd be easier to take your current and calculate the counter EMF than the other way around. But I think you get the idea. The resistance of the armature, the counter EMF, and the motor as the applied voltage, the armature current. I don't want you to get excited here. No, we're not going to be doing calculations.
Oh, man.
My idea here is to let you understand what's happening, why things are changing inside that motor as it becomes inrush, spikes up, and then drops down. Why? Because you get that counter EMF being developed. Okay, so what's the effective in this case? You can look at the inrush current.
So should we read the problem?
No. Yeah, go ahead.
An armature of a 250 volt DC motor draws 15 amps when operating at a full load and has a resistance of 2 ohms. Determine the counter EMF produced by the armature when operating at full load. So here we're just going to insert what they're given to us from what we have. So notice the first thing they did was manipulate that formula because we're trying to find the CEMF. So we had to do a little formula manipulation. Then we're just going to put in our values. So our volts we said was 250, and when we're going to now subtract the amps times the ohms. In this case we had 15 amps multiplied by 2 ohms. 15 times 2 is 30. So we subtract that 30 from the 250, giving us a total voltage of 220. Ta-da.
Ta-da. Okay. All right. At the moment a motor starts, the armature is not rotating, so that no counter EMF is being generated. Only the low resistance of the armature limits the amount of current, or what they call locked rotor current. As the motor picks up speed, a counter EMF is generated in the armature, which opposes the applied terminal voltage and quickly reduces the amount of armature current. At full load speed, the counter EMF nearly equals that of the applied voltage.
And that's with no load.
When a load is applied to the motor,
Its speed will decrease, which will reduce the CEMF, and more current will be drawn by the armature to drive the load.
okay,
Sounds good?
which is what? Slip, right? It's trying to go at full speed, and that torque is preventing it. You'll see that in AC motors also. Armature reaction. Okay, the magnetic field produced by currents flowing through the armature conductors distorts and weakens that of the main field poles. This distortion and field weakening of the stator field is known as armature reaction.
Now it shows a picture of that coil, but it's not like a spring that we think of, right? It's kind of,
No, it's
Yeah.
wraps.
yeah, it wraps around there, so totally different.
The position of the neutral plane. Neutral plane, right?
Neutral meaning it's not towards either the north or the south, right?
Right. Backwards opposing the direction of rotation under no load and loaded motor operation conditions. The no load neutral plane position, the loaded neutral plane position.
So as soon as you have a load, it kind of shifts towards one of those poles, it looks like,
Yeah.
right?
Essentially. I don't want you to get hung up on this though. To me, this is interesting, but not something I'm going to test you on. Armature effect. The armature reaction affects the motor operation by the reduction of motor torque due to the weakening of the magnetic field, arcing at the brushes due to short circuiting of the voltage being induced in the coils under commutation. In large DC motors, interpoles are placed between the main field poles to minimize the effect of armature current. Again, interesting, don't get hung up on it because this is a little bit above and beyond what I expect you to understand. I don't care if you understand how the motors are built. Speed regulation. Speed regulation is basically how well it maintains its speed under load. Ability to maintain its speed from no load to full load without a change in the applied voltage. Okay, the lower the regulation, the better the speed.
So it's almost like you're doing a change in percent there. So you're taking the no load speed minus the full load speed, take that number and divide it by that full load speed, and then you're multiplying by 100 to turn that decimal to a percent. Because you got to move that decimal 2 places to turn it into a percent.
Now, that's hard to get your grasp, how to get a grasp of when you're looking at a DC motor. But when you're looking at an AC motor, it's a little easier to grasp because we've talked about the fact that a no load or the synchronous speed of being, for example, 3,600 RPM, and that its full load speed might be 3,500 RPM because you get slip as it's picking up that extra load. And that's what they're talking about there.
So you're basically talking about the change in the load over the original load.
The change in the speed
Or the change in the speed.
as a function of picking up additional load. You see that obviously the best speed regulation was from the DC motor, what kind? The shunt field, right? The worst was from the series, and in between was compound.
Not too bad. Yay.
Your turn.
All right. We got another problem. Let me kind of zoom in just a little bit better for you. All right. So we have a DC shunt motor is running with a measured no load speed of 1775 RPM. When the full load is applied, the speed drops slightly to 1725 RPM. Find the percent speed regulation. So again, we're going to find that difference first. So we're going to take that no load speed, which is 1775, and subtract the 1725 from it, right? That's our full load speed. So what's the difference there? 1775 minus 1725 is 50. And then we're going to put that over the original, which was the 1725. So 50 divided sign 1725 equals, and then you're to multiply it by 100 to put it in a percentage. That gives us 2.9%.
And realize that the shunt motor, very good speed regulation. Do they give us another one? No.
Just takes us on to the very end DC motor speeds.
All right, so the base motor, day speed of a DC motor nameplate is an indication of how fast the motor will run with rated armature voltage and rated load amps at rated field current. DC motors can be operated below base speed by reducing the amount of voltage applied to the armature, and above rated speed by reducing the field current. Maximum power speed will also be listed in the nameplate. Here's the bottom line, guys. Interesting information. I don't care. Okay, I'm not going to test you on this.
But it does say to use caution, right? We should probably mention that.
Caution: operating motor above its rated maximum speed can cause damage. Again, what's it saying? You got a series wound motor. Make sure that you've got some load on there so that it doesn't take off one, because it literally will blow itself apart.
And that's never a fun situation to be in.
Okay, so I'm not going to get into any further on this. It's interesting. You guys feel free to read through it, but I'm really not going to get into any more on this because I'm not covering it as far as your the information that I expect you to learn from this class. DC motor drives, again, not quite the same as AC motor drives, like variable frequency drives. They're very popular today. Are intended to start and accelerate motors to a normal speed and provide protection against overloads. I'm not going to get into them because, again, it's a lot more information than I have time to cover. All right, it's there. Take a look through it. Feel free, but I'm not going to be testing you on it. Okay.
A little flow chart.
Whole bunch of Zim information there. Typical DC drives used to provide control over the operation of a conveyor system, in addition to, like I say, you get into it, there's information here, but nothing I'm going to cover. Okay? Not intended to blow it off, it's just beyond what I think you really need right now. So with that in mind, got 2 more chapters to cover, so I'll see you in a little bit.